Alrighty, good morning, lads and ladies. Welcome back to MAC2312, which is Calc 2. Today, what the hell are we doing today? Today, we're talking a little bit more about trig sub, right? We're going to continue and finish section 7.3, which is a good section, plenty challenging. We've seen a little tiny taste of it, but today we will see the bulk of it. And if there's time, I'll also introduce section 7.4 on partial fractions. Alrighty, let's do the thing. Here goes. Now, as always, this is MAC 2312. The section number is 004. This is a Calc 2 class, and today is the 15th of September 2021. The plan for today, we're going to finish section 7.3 on trig sub. And then we might begin section 7.4, which is on partial fractions. Just out of curiosity, because when I took these classes, partial fractions was something you learn in pre-calculus. It's a purely algebra thing. And then when you got to this point in Calc 2, the professor is like, okay, you guys remember partial fractions. Well, now we're going to use it here, blah, blah, blah. So I would like to just get a little feedback from y'all. Who has seen partial fractions in pre-calculus? I know we don't usually do it here at Santa Fe. But depending on where you are, who has seen partial fraction decomposition before? Just give me like a thumbs up react or whatever, any react, I don't care, just a reaction. Okay. So just two of us. All right, so we're gonna have to go through partial fractions in detail, that's fine. Let's do the trig sub thing. So remember your trig sub Bible. That says if your integrand contains an expression of the form I'll put here, then you should make the substitution that I'll put down here. If your integrand contains an expression of the form a squared minus u squared, then you should substitute u equals a times the sine of theta. So u here, remember, is allowed to be any linear function of x. U could be like 2x or x plus 5. So if this was like 1 minus parentheses x plus 5 squared, you would substitute x plus 5 equals 1 sine theta. If you have something like a squared plus u squared, like 1 plus x squared or 4 plus 2x all squared, then you would substitute u equals a times the tangent of theta. And if you have a square root of a difference of squares, like u squared minus a squared, then you would substitute u equals a times the secant of theta. This is your trig sub Bible. And like your Lipet rule gets you out of most problems in integration by parts, the trig sub Bible will get you out of most problems in the trig sub section. Not 100% of the time, but 99% of the time, this is the game. We're making substitutions in integrals, which means each time you do this, you're gonna have to calculate a differential. If you're looking at a definite integral, you're going to have to change your bounds. And if you're looking at an indefinite integral, we know from the example we worked at the end of class last Friday that you're going to have to draw a triangle and use some trig identities at the end. Okay. So this is a place for you to flex your trig muscles. All right, you're going to show me what you remember from your 1114 or 1147 class. It is such an important technique that it's one of those things I have to be kind of gatekeepy about. If you don't learn trig sub, I can't really like fast you through the class. You got to learn trig sub, right? Just like you got to learn U sub, you got to learn integration by parts, you got to learn trig sub. It's one of these fundamental things. Can't get through Calc 1 without knowing the power rule. Can't get through Calc 2 without trig sub. Example problems are all over the place, but if I start generating them randomly, I can't guarantee that I won't write something down that is not totally intractable. So let me pop your textbook here. Now your textbook has the trig sub Bible in it, but they've got some extra things in here. You may want to study these. Remember, each of these things come with a domain restriction, right? Because we're interested in a handful of things. First, we want the square roots to simplify nicely. So I don't want to have to worry about absolute values. So I want to make sure that the functions in question are positive. Also, we're going to end up using inverse trig quite a lot here. And each inverse trig function has an associated domain restriction that we need to be mindful of. And that's what they're listing here. And the far right column is the identity that makes that substitution useful. This is just a rewriting of sine squared plus cos squared equals 1. And each of these are the Pythagorean identities just rewritten to isolate the term in question. All right. We started this one in class last time, right? Did we didn't finish this?
No, we didn't.
We did not, right? But we did start it. Okay, let's do it. So that was the integral of the square root of 9 minus x squared all over x squared. So what I should do is first look at the integral. I do have a square root of a quadratic here. So it looks like something from my trig sub Bible. I should ask if I could get away with a u sub instead. Could I sub for the inside of this radical, 9 minus x squared? No trig sub, just u equals 9 minus x squared. Well, that would mean I have to have like a 2x out here, or at least an x out here upstairs that I could cancel with the differential. And since I don't have that, I got to do the trig sub. So u here is just x, a here is 3, right? Because this is like a squared minus u squared. So the sub is x equals 3 times the sine of theta. That's the substitution we make. And remember, this is like a backwards substitution. My old variable is over here. My new variable is inside over here, which means that it's going to be easier to make this substitution go rather than having to like solve and cancel something for the dx. I'm just going to plug in. I do need to calculate dx. dx is 3 cos theta d theta. Now, the other thing I like to do while I'm here, if this was a definite integral, we would change bounds. Since it's an indefinite integral, I know I'm going to have to draw a triangle at the end to go back to my original variable. So let's draw that triangle now. Let's get that out of the way. So if x is equal to 3 sine theta, that means sine theta is equal to x over 3. And I can think of the x as the opposite, 3 as the hypotenuse. So I can draw a right triangle with internal angle theta. And then just by the definition of the sine function, I can say, okay, sine is the opposite over the hypotenuse. That means x is the opposite. And 3 is the hypotenuse. And then you have to solve for this missing side. You know, this squared plus this squared equals this squared. So this thing has to be the square root of this squared minus this squared. So I like to draw that triangle right away. Just get it out of the way. The first two sides you get from your substitution, right? You take this substitution, isolate the trig function. Here we get sine theta equals x over 3. Then you interpret that using your SOHCAHTOA rules, right? Sine is opposite over the hypotenuse. So your opposite is x, opposite theta, and your hypotenuse is 3, opposite the right angle. And then you solve for the missing side. All right, we had to solve for this. This wasn't given to me, but it's easy to solve for. You've done this right triangle bullshit a million times. So now we have everything we could possibly need. Upstairs, the square root of 9 minus x squared becomes the square root of 9 minus 3 sine theta squared. And downstairs, x squared itself is 3 sine theta all squared. And then dx, don't forget this, dx is 3 cos theta d theta. People forget this shit all the time. And I've been bad, I used parentheses there, but I didn't use them here. You should always put the inside of your trig functions in parentheses. It's just good notation. Okay, we went through the first few steps of simplifying this last time. But I suppose there's no harm in going back through it. This will be 9 minus 9 sine squared theta under the radical. Downstairs here, this will be 9 sine squared theta. And this is 3 cos theta d theta. Upstairs, within this radical, I can factor the 9. Some fresh paper. So that's 9 times 1 minus sine squared theta under my radical. Downstairs is still 9 sine squared theta. And over here still 3 cos theta d theta. You'll notice that I'm not in a rush to try and simplify these constants because I want to see how he's going to interact with it first. So just take the time to simplify the radical first. All right, that's the goal here. The challenge, the whole reason this integral sucks, the whole reason I look at this and I go, ooh, is because of the square root upstairs. Right? That's why I can't give this to a Calc 1 student. Without the square root, just 9 minus x squared over x squared, I could totally give that to a Calc 1 student. So the radical is the challenge, which means we should focus on resolving that first. And that's the point of the trig sub, is to clean up the radical. So walking back through here, I just plugged in 3 sine theta for x. Here to here, I squared 3 sine theta top and bottom. That gives me 9 sine squared theta here and 9 sine squared theta down here. I don't really care about this guy for now. I'm just working on the radical. The radicand, the thing under the radical, is 9 minus 9 sine squared theta. Those two terms both have a factor of 9 that I can factor out. And when I do, I get 1 minus sine squared theta, which is nice because 1 minus sine squared theta one minus sine squared theta is cos squared theta by the first Pythagorean identity. So this is equal to the integral of square root 9 cos squared theta over 9 sine squared theta all times 3 cos theta d theta. And the magic is that this radical no longer has any subtraction or addition in it. It's just multiplication. Radicals may not play nice with addition or subtraction, but they do play nice with multiplication and division. So I can take the square root of the 9 and the square root of the cos squared separately. So that top is now going to be 3 cos theta. Squared theta switch on downstairs and 3 cos theta d theta at the end. Now we can combine these. 3 cos theta times 3 cos theta is 9 cos squared theta. Downstairs I have sine squared theta. So I'll write this is 9 cos squared theta over 9 sine squared theta d theta. The 9's cancel. Cos squared over sine squared is cotangent squared. And I'm going to pause here for a minute because this is really the bulk of the new work, right? So all of the stuff that is kind of native to trig sub has been done. The integral of cotangent squared, that's a 7.2 problem. That's a trig integral problem, not a trig sub problem. All the trig sub is done. So if you're good up to here, then you've understood the 7.3 content. So I think it's worthwhile to take a second, pause. Any questions from how we get here, through all this stuff, through the triangle, through all this stuff, down to here? Yes, please. Go ahead.
Sorry, when you make that triangle, it makes the square root of 9 minus x squared, which resembles the initial part of the problem. Is this like a pattern we could expect to see in certain kinds of problems, or is this a coincidence?
Not a coincidence. Is a pattern you can expect to see. Not 100% of the time, but 90-ish% of the time. Basically, anytime you're doing the trig sub because of a square root like that, your missing side of the triangle will be that square root that told you to do the trig sub in the first place. So anytime the trig sub Bible gets you out of trouble, the missing side of your triangle will be the square root from the trig sub Bible.
Okay, thank you.
Yeah, of course, of course. It's a good question. It's a good observation. Any other questions up to this point? Okay then. So the fun part now is how do you integrate cotangent? Or how do you integrate cotangent squared? I'm just going to bring it up here, save some paper. Anybody? What if it was just regular tangent squared? This one's a little bit tricky. It's a little bit tricky because it's actually kind of too easy, right? I think most of our brains are looking for the like substitution we could make or the way to split it up and use some other trig identities. It's actually simpler than that. If I divide both sides of this identity by sine squared, then I get cosecant squared theta minus 1 equals cotangent squared theta. This is another form of your Pythagorean identity, which of course you all know by heart. So I can rewrite the integral of cotangent squared as the integral of cosecant squared theta minus 1 d theta, which is nice to do because I know somebody whose derivative is cosecant squared, and I know somebody whose derivative is 1. What is the antiderivative of cosecant squared?
So natural log. No.
Now, if
Secant.
it's just cosecant, then that would be a natural log of cosecant plus cotangent. Negative natural log cosecant plus cotangent. But this one's easier still. Oh, so let me ask a related question. What's the derivative of tangent?
Tangent. Tangent squared theta.
Derivative of tangent is secant squared, right? And the derivative of cotangent is negative cosecant squared. So this is something from the table in 5.4. This is negative cotangent theta. And then the 1 d theta is going to integrate to theta. So some trig derivatives running in the background here that we don't use all the time, but we use certainly enough that you should know them. If you're ever in trouble, struggling to remember it the way I do this, I never forget the derivative of tangent. The derivative of tangent is secant squared. We use that shit all the time. That means that the derivative of cotangent is negative cosecant squared, which means that the integral of cosecant squared is going to be negative cotangent. So that's this. Now we need to go back to the original variable. All right, this is an indefinite integral. There's no bounds for us to plug in, which means we have to answer in terms of the same variable that we started with. My reader wouldn't know what theta is. If I just told you the integral of square root 9 minus x squared over x squared is negative cotangent theta minus theta, people will be like, what the fuck is theta? So we use our triangle to go back to the x's. The cotangent of theta can be read off from this triangle, right? Tangent is opposite over adjacent, so cotangent is adjacent over the opposite. That's negative cotangent, that negative is this negative. Opposite over adjacent would be x over the square root, so adjacent over opposite is the square root over the x. And then minus theta. Well, what is theta? We saw this the other day. If sine theta is x over 3, then theta is the inverse sine of x over 3. And plus c is plus c. Okay, so this is that problem sorted out. And this is a pretty typical trig sub problem. This is about the caliber problem you can expect to see on the test. You'll have some in the homework that are a little bit more involved, but as far as test level problems, this is about there. Questions on any of these pieces? Okay, let's grab some more. What else is good? The ellipse is fun, but it's a little tricky. Let's do this one. Not there. Yeah, this is good. So I have here the integral of 1 over x squared times the square root of, focus you fuck, x squared plus 4. This radical does look like something from my trig sub Bible. What's the substitution I'm going to make here?
Tangent x.
Careful, so remember the new variable is going to be the inside of our trig function. I can't use x again. We could use something other than theta, but we have to use a different letter than the letter that's in the original. It is going to be a tangent, but there's a little bit more to it than that.
The 4 in the front, the 4 tan of theta.
2 tangent theta.
Yeah, so Daniel got it there. It's going to actually be x equals 2 tangent theta. So remember, we have to think of this as x squared plus a squared. So 4 is a squared. That means a is 2. So we're going to sub x equals 2 tangent theta. And remember, the idea is when we plug in here, we're going to have to square the result, and we want to be able to factor the 4 out. So the thing that we have to put in front of the tangent isn't the constant there, it's the square root of that constant. Dx then is going to be 2 secant squared theta d theta, and we can draw our triangle. If x is 2 tangent theta, then tangent theta is x over 2. So I can think of this as my opposite, and this is my adjacent. So I draw a little right triangle with internal angle theta. The opposite side is x, the adjacent side is 2. And then as in the previous problem, the missing side, which in this case is the hypotenuse, if you solve for it, this squared equals this squared plus this squared has to be the square root of x squared plus 4. So there's everything I'm going to need for this substitution, all in one handy dandy place. Nice to get that out of the way. Now we just plug everything in. Everywhere there's an x, I write 2 tangent theta. And for dx, I write 2 secant squared theta d theta. So this becomes, I'll put the 2 secant squared theta d theta upstairs, or at least the 2 secant squared theta. Downstairs here, x squared, that's 2 tan theta squared. And the square root is 2 tan theta squared plus 4, and then d theta chilling. Okay. And this might look a little scary, but we know this piece is going to clean up really nicely. Let's see how it cleans up. The focus should be on the radical. So 2 secant squared upstairs. Good fraction. This is 4 tan squared theta, 2 tan theta all squared. And then the square root here is 4 tan squared theta plus 4. And d theta chilling. I'll say again, one of the most common places I have to take points off for this stuff on tests is forgetting to plug in the differential, forgetting this 2 secant squared theta d theta. If you ever find yourself writing thetas here and dx here, you've made a mistake. This is one of the many reasons we need to always be in the habit of writing our differentials. It can tell us, oh shit, I forgot to do something. How do I clean up this square root? Let's do it off to the side.
Factor out of 4.
Yeah, very good. So the square root of 4 tan squared theta plus 4. We factor of 4, and that's leaving now tan squared theta plus 1, all under the radical. So that's 4 times, what is tan squared theta plus 1? Think to your Pythagorean identities. Maybe you see it more.
Secant
Secant.
squared theta.
Secant squared, right? So we have here the square root of 4 secant squared theta, which is just 2 secant theta. Isn't that magic? So my integrand, I've got the 2 secant squared theta upstairs. Got 4 tan squared theta downstairs. And the square root of 4 tan squared theta plus 4 is 2 secant theta. D theta chilling. Maxwell. Maxie, no. Sorry, dog's got a little worked up. All right, so I can cancel this secant with one of these secants. 4 times 2 downstairs is 8, 2 upstairs is 2, 2 over 8 is 1/4. So I'll pop out the 1/4. One of the secants upstairs goes. And I have secant theta over tangent squared theta d theta. How do I do this integral? Anybody?
Maybe change it into sines and cosines.
Very good, right? This isn't like secant, power of secant times power of tangent. It's a power of secant divided by a power of tangent. So this doesn't fit neatly into our model of how to do trig integrals yet. So we should rewrite it in a way that it could fit into that model. And the easiest way to do that, just break it down into sines and cosines. So secant is 1 over the cosine of theta. And that's my numerator. Tangent squared is sine squared theta over cos squared theta. D theta is d theta. And when you see a fraction like this, you know what to do. You leave the top alone, you flip the bottom. So this is 1 over cos theta times cos squared theta over sine squared theta d theta. You can cancel the cosine. You have 1/4 integral cos theta over sine squared theta now. And I'll tell you, there's more than one way to skin this cat. One way of looking at this, my preferred way of looking at this, is as cosecant theta times cotangent theta. I like that. Right? 1 over sine is cosecant. Cosine over sine is cotangent. This is different than how your book does it. You can also do this with a little u sub. Oh, I forgot the 1/4. So I'll write this as 1 over sine theta times cos theta over sine theta d theta, because that, all right, first observe sine squared downstairs, sine times sine downstairs, that's sine squared, cos upstairs, 1 times cos is cos. 1 over sine is cosecant. Cos over sine is cotangent. Whose derivative is cosecant cotangent? Let's see, I'm catching you guys out on these trig derivatives. You're scaring me a little bit.
Is it cotangent?
Not quite. So again, this is one of them that I remember by thinking about the non-co version, right? So like the integral of cosecant squared that we needed a second ago. I think, okay, I know the derivative of tangent is secant squared, so the derivative of cotangent is negative cosecant squared. There's that pattern between the regular function and the cofunctions, derivatives kind of matching up, but with negatives. Same shit will work here. I know the derivative of secant theta is secant theta tangent theta. So the derivative of cosecant theta is negative cosecant theta cotangent theta, which means that the integral of cosecant cotangent is negative cosecant. So this is negative 1/4 cosecant of theta plus c. I recognize that trigonometry here at Santa Fe sucks balls. Facts. I recognize that Calc 1 teachers here at Santa Fe are sometimes afraid of trigonometry. Holy fuck, it's scary, but it's true. You're going to be an engineer, physicist, chemist, any sort of thing where you're using geometry and mathematics regularly in your work. You gotta be a badass with trig. It's not a maybe, it's not something you can be scared of. It's something you need to be a badass with, and you can do it. It's not that hard, but you just need to practice. Make sure you know these derivatives, right? All of them. Make sure you know everything from that table in 5.4, all of it. This is all right there, right? Integral of cosecant cotangent, right there in that table. Flashcards work, but they're boring. The best way to get this stuff is to solve problems. So I know I'm deviating a little bit from the lesson plan here, and I'm sorry for that, but I want to show you a way you can practice these things. If you go back one section to 7.2, right, where we're looking at powers of sine, powers of cosine, powers of secant, powers of tangent, the homework problems I assign you guys are the bare minimum. That's really how you should think of it. There's a lot more here, like a lot more. And I'll tell you, when I took mathematics classes like calculus, I did my best to solve every single problem in these sections. And that's how you become a badass. So anything and everything that you're worried about, you can come in here and practice it until you're a beast. And it's not going to kill you. The odd numbered exercises have answers in the back. There's a student solutions manual. And if you're ever stuck or curious, send me a message. I'm happy to talk with you. If you work all the problems in 7.2, nothing will scare you in 7.3. I promise you that. It's the best way to kind of recap this stuff if you happen to forget it, and to never be afraid of this stuff. It is a big time commitment. So, you know, if trig is scaring you a little bit and you feel like Santa Fe kind of boned you by not pushing you hard enough with trig in 1114, 1147 or Calc 1, now's the time to fix that. And make sure that wherever you're going in the future, I know most of you guys are planning to transfer either to UF or some other university, the best way to come in there with confidence is to fill those gaps before you get called out for them. Trust me on that. I also went to community college, transferred to university. It was a little brutal that first semester. So be ruthless about your practice here. Come in and solve these 7.2 problems. If you need a copy of the book, you can leaf through more easily. I can get you this PDF, just let me know. All right, integral cosecant cotangent, negative cosecant, the 1/4 comes along for the ride. Here's the negative. We're not quite done though, because they asked me about x's. So I got to tell them about x's. I can't tell them about thetas. Remember that cosecant is 1 over sine. So the cosecant of theta's geometric interpretation is the hypotenuse over the opposite, right? Sine is opposite over hypotenuse. So cosecant, the reciprocal of sine, is hypotenuse over opposite. So I take this hypotenuse right here, and I divide it by this opposite side right here, and that is your cosecant theta. So this is negative 1/4 times the square root of x squared plus 4 divided by the opposite side length, which is x. And then you tack on your plus c and you declare victory. All right, that's the problem. These are good for scaring grandparents, little brothers, things like that. But the truth is, every single step is very straightforward. There's no magical hand waving, cross your fingers, hope, none of that. It's all super, super consistent. So if you practice, you will be in very good shape. All right, take a second, look at your notes, look at my work. What questions do we have? Feeling good? This would be another example of an exam caliber problem. This is about the level of trig sub problem you can expect to see on our tests. You want to be grinding these out no more than 10 minutes, something like that, right? In the 10-minute range. Here we've gone through and explained everything in about 12 minutes. You want to be able to crunch these out at a reasonable clip. The next problem I'm going to show you is not an exam caliber problem. It's definitely a homework caliber problem because it's more involved. But it gives me an excuse to see if you remember how to complete the square, and to just talk a little bit about completing the square. Not an exam caliber problem. What's weird about this compared to the other ones? Focus.
There's an extra x in the 2.
Yeah, if that was just x squared plus 2, I would let x be the square root of 2 times the tangent of theta and grind my little titties off. But it's not. It's x squared plus 2x, which doesn't look like anything from my trig sub Bible, right? How do you make something like this look like something from that trig sub Bible?
Factor out an x.
Well, if I good thought. Okay, if we factor out an x, then this would become this, which is still not looking like anything from the trig sub Bible. I need like some linear function of x squared plus or minus a constant. So while that's correct, it's accurate to say that x squared plus 2x is equal to x times quantity x plus 2. It's not moving in the direction we want.
Maybe change the square root into an exponent. I don't know if that'll do anything with the x squared.
Does not. So the square root symbol behaves exactly the same as the exponent for precisely the reason you're suggesting is that they mean the same thing. So rewriting this as a 1/2 power, again, true, but not helpful. I need to do something inside. I need to do something to the x squared plus 2x to make it look more like the stuff from the trig sub Bible. And the magic words here . Complete the square. So x squared plus 2x can be written as a perfect square plus or minus a constant. And the trick to doing that in this case is to add 1 and subtract 1. Mathematicians' favorite tricks are always the dumb ones, right? Multiply by 1, add 0. I'm adding 0. I'm just adding 0 in a way that is like a little bit suggestive and useful, because I know that x squared plus 2x plus 1 is a perfect square. That's x plus 1 squared. And this minus 1 is this minus 1. I have a whole thing on completing the square in your modules. This is something I know that is in Santa Fe's pre-calculus classes officially, but unofficially, I have a feeling not everybody gets to it. So I think it's in the trig subsection. No, completing the square. Where is it? I know it's in here. Is it its own thing? Resources for this, convergence, indices. Oh shit, do I not have that in here? There it is, there it is. Yeah, it's under trig sub, completing the square. All right, that's gonna be weird. So this is actually a document I made myself for you guys. So it's all about how to complete the square. The basic idea, you can always add 0. No one can stop you from adding 0. That's what I've done right here. I took x squared plus 2x and I added 0 in the form plus 1 minus 1. In general, the thing you're going to add is b over 2a all squared. Now, in this document, I use completing the square to prove the quadratic formula. If you've never seen that, you should go through it. It's beautiful. You should write it down along with this, right? It's not a hard thing. But then we've got lots of examples of completing the square here. So we're going to complete the square in this. We're going to complete the square in this. We're going to complete the square in this. And then there's an example using an integral that is very similar to the one we're working now. So if you don't remember how to complete the square, save a copy of this document, please. Work through it. You're gonna need this. This sort of thing, The reason we cover this in this class is because they show up a lot in physics, surprisingly often. So it is a necessary thing. I think I remember using this when discussing a pendulum in physics 1 and discussing the magnetic field induced by a current through a rod in physics 2. These will show up. So we complete the square under the radical. That's our first step. And that gives us the square root of x plus 1 squared minus 1, like this. Now remember what I said in the trig sub Bible? U is any linear function of x. So the gain here, oh, I lost it. Oh. You could make the actual substitution u equals x plus 1. And then this would become the integral of u squared minus 1. But rather than doing that, we can just go ahead and sub. So this is like your u in the trig sub Bible. So the move here is going to let x plus 1 be equal to something. What is the something here? If this was just x squared minus 1, what would the sub be? Go ahead, look back. Look at my notes. If I have the square root of u squared minus a squared, then we sub
X plus 1 secant theta.
yeah. Yeah, my a here is this 1. So I'm going to let u, which is x plus 1, be equal to a, which is 1 times the secant of theta. Now, taking differentials on both sides here is not hard. You just differentiate on the left, differentiate on the right. The derivative of x plus 1 is 1. So this is 1 dx, or just dx, equals the derivative of secant theta is secant theta tangent theta. So that differential is secant theta tangent theta d theta. We will also draw our triangle at this stage. Secant theta is x over 1, or sorry, x plus 1 over 1. So that's the, let's see, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So this has to be hypotenuse over adjacent. I may have to pause here in a second and yell at the dog, I'm sorry. So I draw my triangle. It's a right triangle, internal angle there is theta. The hypotenuse is x plus 1. The adjacent side is 1. And the missing side here is going to be the piece from the square root. Or you can just calculate it using the Pythagorean theorem, right? This squared plus this squared equals this squared. Maxwell, no puppy. You literally eating your mom's homework right now? Well, he chewed on the IBP notes. Just a little bit on the corner. I got him. Okay, they're on the kitchen table now. So we've got all of our substitution stuff here. I'd like to take a second and just make sure we're comfy with what this substitution is and why we're making it, how we calculate the differentials, anything like that. All Gucci? X plus 1 is secant theta. So this is the square root of secant squared theta minus 1. Dx is secant theta tangent theta d theta. So that is the result. Secant squared minus 1, what's that?
Tangent squared theta.
Good. So this is the integral of the square root of tan squared theta times secant theta tangent theta d theta. And it's about to get better. Square root of tangent squared is tangent. Tangent times tangent is secant times tangent squared. And all of your stomachs should just have dropped. Why is this unpleasant?
Because the square.
Yeah, that's one way to say it. This is an odd power of secant times an even power of tangent, which is not the nice case. It's not either of the nice cases. This is that unpleasant looping IBP case. Now, conveniently, we've done this integral before. This is 1/2 secant theta tangent theta minus the natural log of secant theta plus tangent theta plus c. And the procedure to go from here to here is an unpleasant one. Did this last week. It's a looping IBP problem. I had to use some trig identities. So rather than taking up your class time by grinding this integral out again, because we've already done this exact integral 2 different ways in class, we did it once by the direct looping IBP approach, and we did it once by turning it into the integral of secant cubed minus the integral of secant. Both yield the same thing, of course. So I'm not going to go back through that. But just to give you an idea of how gnarly these problems can get, right? You had to complete the square, then trig sub, then looping IBP. That's rough. Finally, we go back to the original variable. These are thetas. The magic thing for that is the triangle. So secant of theta is x plus 1. And it's the hypotenuse over the adjacent. So this is 1/2 times x plus 1 times the tangent of theta is the opposite over the adjacent. So I'll write it as it is in the triangle. Minus the natural log of the absolute value of x plus 1 plus the tangent, which is the square root of x plus 1 squared minus 1. Plus. So undeniably a rough problem here, right? Not something I would give you on a test, but it is something that shows up in the real world. And it's something we need to be able to manage. Mathematicians are the sort of people that say, oh, I can reduce this problem to one I've solved previously, therefore I don't need to do anything. But if you're an engineer, physicist, whatever, you need to do the thing, right? You gotta have the numbers. So this is the game. Good news, this is about as bad as these problems get. You won't find anything in section 7.3 that is worse than this. You will find some things that are equivalent to this, right? There's many trig subintegrals that drop out to secant cubed. There's many trig subintegrals that drop out to an odd power of secant times an even power of tangent. As much as we abhor those things, we have to know how to deal with them, and this is how we deal with them. But the goal for us today is to get comfy on all the work that gets us up to this. Everything after this is stuff we did last week. So questions on any of this stuff? Okay, not too bad. Let me see where we're at with time. 10:25 is a 9:30 to 10:45. I can show you a few extra things. There are some integrals where this technique is useful, even though even though there is no square root. So depending on how well you've studied that table at the end of section 5.4, you may or may not know what this integral comes out to. If a is 1, then this is 1 over x squared plus 1. We should remember that at least is what? What's the integral of 1 over x squared plus 1? One of our basic integrals. It's the inverse tangent function. Inverse tangent function. There is a more general formula in the textbook. Oh no, they don't have the more general one here, but right, yeah, this guy. And then later in section 7.5, there is a more general formula. All right, so 1 over x squared plus 1, you integrate that, you get the inverse tangent function. That's a special case of this, right, where a is just equal to 1. If you want to evaluate an integral like this in general, you do it with trig sub. So this piece, even though it's not under a square root, looks like the thing from our trig sub Bible, right? If this was under a square root, then the trig sub Bible would say let x equal a times the tangent of theta. Dx then would be a times secant squared theta d theta. And it happens that for this problem, we're not going to need the triangle, so I'm not going to draw it. But yeah, you wouldn't know that a priori. Here I would have 1 over this stuff times the differential. I'll put the differential upstairs like we did on the last problem. And then downstairs, x squared plus a squared, that's a times the tangent of theta all squared plus a squared, and your d theta is over here. The a secant squared theta is coming from the differential. Downstairs, this is a squared tan squared theta. So this is a secant squared theta divided by a squared tan squared theta plus a squared d theta. What would be a good next step? If this was all under a square root, what would we do next?
Factor out on a squared,
Yeah,
and then change with trig identities.
very good. Let's do it. So this is a secant squared theta divided by a squared times tan squared theta plus 1 d theta. And tan squared theta plus 1, now I've got a, I'll leave it like this for now, a secant squared theta over a squared. Tan squared theta plus 1 is secant squared theta. So those cancel. A over a squared is 1 over a. So I have 1 over a times the integral of d theta. Secant squared over secant squared is 1. Which is 1 over a times theta plus c. So if x is equal to a tan theta, that means tan theta is equal to x over a, which means theta is the inverse tangent of x over a. So this is 1 over a times theta, which is the inverse tangent of x over a plus c. And this is something I actually recommend that you commit to memory. Right. you'll see a lot of integrals of this form, like a lot, especially in the next section, section 7.4, partial fractions. These things show up quite often. And in order to manage them quickly, you don't want to have to go through this whole trig sub procedure every time you see one. Just know that an integral of this form is always this. This is part of why I'm so into the inverse tangent function. It shows up a lot. It's also got some really nice properties. So that's the end of our lesson on trig sub. In the few seconds I have left, I'm going to try to motivate partial fractions a little bit. How would I do an integral like this?
The difference of two squares.
It's true that that is x squared minus 1 downstairs. And you could maybe try to sneak in a secant substitution, like a trig sub thing. But remember, the integral doesn't play nice with like multiplication, right? Let me get away from the difference of squares thing. How about just x times x plus 1? You see, the issue is that I can't like split up a fraction over its denominator, right? There's no nice, obvious way to split this integral up. If it was just 1 over x or 1 over x plus 1, those I know how to handle. So wouldn't it be nice if we could relate these to the 1 over x times x plus 1 dx integral? I mean, I'll answer the question. Yes, it would be nice if we could. It would be nice. And we can. We can, but it's not obvious. It is a fact of linear algebra, which is, remember in pre-calculus when we studied like matrices and stuff? It is a fact of that area of mathematics that a rational function like this is a rational function, this is a rational function, a ratio of two polynomials, can always be split up over the factors of its denominator. It's really just a consequence of the whole common denominator practice. So it turns out that for some constants, call them capital A and capital B, that 1 over x times x plus 1 will be equal to A over x plus B over x plus 1. You have to ask yourself, what sort of things could I have added up to get this? What sort of things, such that when I put them together with a common denominator, could give me something over x times x plus 1? Well, if I take something over x and I add that to something over x plus 1, then when you go to combine those two fractions, you would have to have a common denominator, right? And that common denominator would be x times x plus 1. So it stands to reason that maybe I could take something like this and undo that common denominator process. say, okay, well, what two fractions could I have added up to get this? And the numerator doesn't have to be 1, the numerator could be anything. And then from here, once you kind of accept that that is possible, we can try to solve for a and b. If you cross multiply on both sides, meaning you multiply both sides by x times x plus 1 to kill all the denominators, you get 1 equals a times x plus 1 plus b times x. Which we can then rewrite as 1 equals ax plus bx, which is a plus b times x plus a. Right, just distributing the a here and then combining like terms. From here, what you do is you equate coefficients on both sides. So this left-hand side, which is just 1, I'll write that as 0x plus 1 equals the right-hand side, which is a plus b x plus a. And then you set the coefficients of x on the left equal to the coefficient of x on the right. And you set the constant on the left equal to the constant on the right. And this yields a linear system. A plus b is equal to 0. And a is equal to 1. Some linear systems are hard to solve, not this one though. If a, the bottom equation just says a is equal to 1, and you take that together with a plus b equals 0, so b has to be -1. In other words, what we've discovered that 1 over x times x plus 1 is equal to a over x, which is 1 over x, plus b, which is -1, so minus 1 over x plus 1. Thus, the integral of 1 over x times x plus 1 dx is equal to the integral of 1 over x minus 1 over x plus 1 dx. And then you can split that up as integral 1 over x dx minus integral 1 over x plus 1 dx, and you can carry on from there. This process of splitting up your rational function based on the factors of its denominators is called partial fractions, partial fraction decomposition. And it's a big deal. It's an algebra procedure. There's absolutely no calculus, right? I have done 0 calculus here, just algebra. Pretty simple algebra. But there are a few catches. First, in order to even get started here, the denominator needs to be factored. Sometimes factoring polynomials is hard. Second, in order to even get started here, the degree of the numerator needs to be strictly smaller than the degree of the denominator. If that's not the case, then you need to do polynomial long division in order to rewrite it as a proper rational function. And then the third and most important catch, the factors of the denominator may not always be this nice. Some polynomials factor like this into distinct linear factors. Other polynomials, factors include irreducible quadratics, things like x squared plus 1, or repeated factors, things like x minus 3 squared. Those sort of situations will require some special treatment. But the thing I would like you to walk away from today with is this understanding that you can do stuff like this. Even in nasty cases, there are ways to split up functions like this into simpler pieces. And that procedure is called partial fractions. And the heart of the matter is this step, where you go from here to this system. So take a second and make sure you're really comfy with what we did here. The left-hand side was 1, and I said, okay, that's the same as 0x plus 1. The right-hand side is a plus b times x plus a. So I say, okay, the coefficient of x over here is a plus b. The coefficient of x over here is 0. So a plus b must be 0. The constant term over here is a. The constant term over here is 1. So a must be equal to 1. It's very similar to if I told you like 2x squared plus 3x minus 5 is equal to ax squared plus bx plus c. You would know a is 2, b is negative 3, and c is 5. You're just setting coefficients equal to each other. That'll give you a linear system. Might be easy, might be hard. You want to solve this using elimination as a general rule. If it's not already triangular, then you plug back in and then carry on. So on Friday, I'm going to run you through the details here. On Friday, I will show you all 4 cases for partial fractions. They depend on the factors of the denominator. And I'll also walk you through one example where you're doing some polynomial long division. Unfortunately, I don't have time in this class to go back over all of the pre-calc stuff. So if you've forgotten how to divide polynomials, I've got convenient videos here for you. Check these out, right? If that's something that you haven't done in a long time, if you haven't divided polynomials in a while, you should do it. You should absolutely do it, or at least watch one of these videos. And then on Friday, I will run through some examples and show you the full deal. But that's where we're going, partial fractions. After partial fractions, we're pretty much ready for the test. Say this as well, right? Let's take a look at your syllabus. After partial fractions, there's one more section, which is just strategies for integration. Here we are. So after partial fractions, there's just one more section, which is like a strategy section where they take all the stuff from the previous parts of chapter 7 and roll them together. Once we finish that, it's time for test 1. Okay, so test 1, probably a week from Friday. All right, next Friday. This Friday, we will finish up partial fractions. Early next week, we will go through section 7.5. And then on Friday, I think of next week, you will have your first test. Okay, so we're almost there. We're almost there for test 1. It's not an easy test. It's not, right? We've got substitution, areas, average value, all of those volume problems, work, integration by parts, and all the other integration methods. So make sure you're prepping. Stay on top of this homework. All right, I've gotten a handful of extension requests, and I know that life happens, and I don't have any problem with that. But you need to stay on top of the shit. So if you've let a few things slide, it's time to start catching up and being serious before you're underwater. Exam probably next Friday. Okay, that's it from me for today, guys. I hope you have a lovely rest of your day, and I will see all of you next time.